Hello, everyone. Hope you're all doing well. I'm all bundled up. I cannot get warm today. It's one of those days. I don't know why. And my husband and I like to go for as long as we can without turning the heat on. I don't know. We do the same thing with air conditioning too. It's kind of like a game for us. So we will see how deep into winter we can go. There has been a time we got all the way through like mid-December without turning the heat on. Now we have kids, so we usually have to do it a little bit earlier than that. So we are working through our way through nuclear chemistry. Oops, the slides disappeared on me. Let me open those back up. Okay, so we'll go to the slides in a minute, but I don't want to do half-life just yet. Let's work on that dry lab. We can do a couple of the questions out of there. This is a refresher. Pull it up. You don't have the dry lab printed out. Go ahead and you can pull it up on your computer. It is underneath the lab section in the on the Moodle page. You can also, I'll share screen so we can look at a couple of these. Yeah. All right. So looking at here, let's go ahead and complete these equations. These nuclear equations specifically. So I've got aluminum 27. You can put the little 13 down there too, plus some sort of mystery symbol. That's what we're going to be solving for. Produces sodium 24 and an alpha particle. So we want to figure out what this aluminum got hit with pretty much to produce these two things. So I want you to go ahead and try and work through that, give you just 2 minutes for it. Okay, so for this one here, with all of our nuclear equations, we need to make sure that the top numbers on both sides sum up so that the masses are the same. So in this case, we've got 24 and 4, so 28. That means that this whole component also needs to be 28. 27 are included in the aluminum, so my mystery particle is going to have an atomic mass of 1. Then we have our numbers at the bottom. Those also will need to total each other. So we've got 11 and 2 for a total of 13. This side also needs to be 13, and they're all actually being, that atomic number is being completely used by aluminum. So my atomic number for this thing is going to be 0. So this is talking about, protons or charge. This number is talking about mass. So what has a mass of 1 but isn't a proton? Deep, 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 deep. Do electrons have mass? No. Do protons have mass? Yes. But we aren't a proton. A neutron. Neutron, yes. Neutron, awesome. So the completed mystery particle for this would be a neutron. Let's look at the next one here. We've got iodine 131. Let me clear this out. Let me get my pen back. We've got iodine 131. And what is this thing doing? It's going through a beta emission, right? So this is a beta particle, which is just a high-speed electron. And we want to figure out what it ends up decaying into. So again, our top numbers need to equal each other. This only has 131, so the total over here needs to be 131. 0 of it is occupied by the mass of the electron, so a whole 131 can be in this position here. Now I've got to work on the bottom, 53 here, so the total needs to be 53. This is a -1, so this needs to be 54. 54 plus a -1 is 53. So what's happened here is one of the neutrons has converted to a proton. So then we look up on our periodic chart. Oh my goodness, do I not have a periodic chart? There we go. Okay. So 54, where are you? What are you? Who are you? Xenon. Someone give me help with that in the chat. Thank you. Oh. Okay, so we've got xenon. Okay, come on, admit, those are like a little bit fun to do, right? They're a little fun. It's kind of like a little puzzle. While we're at it, why don't we work on this one too? Because we'll get some of your lab done. So I want you to try this one. You've got 2 pretty large atoms that are getting smushed into each other. They're being bombarded by each other. And one of the things that comes off is a neutron. I want you to tell me what the other component of that is. Okay, so for this one, we've got 96 and 99. So our total mass for the top is 195. So we need to have 195 over here as well. One is occupied by the neutron, so 194. Let's go for the bottom 40, 40, and 42. So we have a total of 82 protons. None of those are being occupied by the neutron, so we can put 82 here. And then we look up our 82, which is lead, P. Yes, no, maybe so. Yeah, not too bad. All right, let's see what else we can do here. We worked on one of those. Let's do this one here. So we've got sodium 25, and I want that to undergo beta decay. So I want you to write out what it would look like if it emitted a high energy electron. Okay, so for this one, and really for like every single one of these, because it's in the section talking about beta decay, you can put a beta particle as the first thing that's emitted. So we've got a mass of 0, charge of -1, and its electron. 0, -1. Deep, 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 deep. All right. Now, the numbers need to be the same on the top. So if 25 is here and this is 0, the next thing also will have a mass of 25. If I'm releasing negative charge, what I'm doing is pretty much taking a proton and converting it back into a neutron. So instead of 11 here, 11 minus the 1 will give us 10. And then we drop to the material before, which is what? Neon? Yeah. All right, and then we do the same thing here. Top number stays the same, bottom number decreases by 1. 7, that's what, nitrogen? Yes. The 92 is going to stay on the top. 38 will become 37, and it's going to be rubidium. Hopefully you're seeing a pattern here. 42, it stays the same with beta emission. 1918, whatever comes before that is, what is that, argon? Yeah, argon. So there, that section should be complete for you. You should get every one of those right. Let's see. I'm not going to do all of them, but let's do, I like C and D. We'll do C and D. So I want you to tell me what the question mark is in those equations. The first one is copper 66, and it decays to zinc 66, and I want to know what the particle is, or what type of, pretty much like the equation is saying, what type of decay is it undergoing. And the other thing says something decays, goes through alpha decay to become thorium-234. What is that initial thing? Oh, hold on. May have made a mistake. Hold on. I may have made a mistake. Yeah, I'm confused too. That's probably because I did something wrong here. What did I do wrong? I totally did that backwards. I'm sorry, guys. I'm sorry. It's supposed to be higher. Yes. Yes, yes, yes. Ugh. My brain today has not been working for me. So let's just scratch everything that I just said. Just get rid of all that. Well, most of it. Oh, yeah. I am so sorry. I hate doing that. Okay, so 11. This is a negative one, so this needs to, in fact, be 12. 12 minus the 1 will give us the 11. This needs to be 9. This needs to be 39. And this needs to be 20. Ay. I was testing your skills, everyone. I was testing your skills. So this is going to be magnesium. This is going to be fluorine. This is going to be, what is that, yttrium? And then potassium will be calcium. So sorry. All right, hopefully that cleared that up for everyone in the class. So we'll do C and D. Lauren, are we going to talk about how to do 9 today? Is that referring to, yeah, half-lives? Yes, we will talk about that today, Lauren. Once we finish these 2 examples, we'll go into half-life and Geiger counters and things like that. Okay, so for this one, top value is 66. 66. So the top value over here also needs to be 66. All of that's being occupied by the zinc. So this mystery particle has a 0 mass. 29 over here. So this needs to also be 29, and we have 30. So this needs to be a -1. So this is beta emission, right? This is what it was supposed to look like on those previous ones. It goes up one. What we have going on here, 234 and 4 for a total of 238. I'm guessing this is uranium 238. We've got 238, 90 plus 2 gives us 92. And yeah, yeah, it is uranium. Cool. Okay, so hopefully we've got those down. Look at the rest of these slides. So radiation, and measuring radiation, how radioactive something is. Here's a gentleman and he has a what's known as a Geiger counter, and it checks radiation levels. So it'll sort of ping every time something decays in it. And if there's a bunch of things decaying rapidly, it'll ping faster. You hear this like sort of staticky sound that increases. So measures beta decay and gamma decay. Doesn't usually measure alpha decay because that, again, that's something that can be stopped with like a t-shirt or a piece of paper. There's a series of electrons in a cathode, and then the radiation will ping at the electrons, and it will produce, usually it produces sort of an audible sound. So some of the measurements for radiation, we have the Curie, or Madame Curie, very, very smart female scientist in chemistry, worked with radioactive material, ended up dying because of radiation exposure. But a Curie is the number of disintegrations that occur in 1 second for 1 gram of radium. So she used radium as her standard, specifically a gram of it. And that is equivalent to 3.7 times 10 to the 10 disintegrations in a second. So it's, you know, it's a relatively large number, 3.7 times 10 to the 10 disintegrations in every single second. We have a becquerel or BQ. This is the SI unit of radiation. And this is equivalent to 1 disintegration per second. We have a rad, which is your like radiation absorbed dose, which is the amount of radiation absorbed by a gram of material, like for instance, body tissue. So how much radiation is, you know, a fat cell going to absorb versus, I don't know, tree bark, something like that. We also have a gray, which is GY. This is the SI unit for an absorbed dose, and it is the joules of energy in a kilogram of body tissue. Another unit, the REM, or radiation equivalent in humans. This measures biological effects of different types of radiation, specifically off of like what it does. So alpha particles, which don't penetrate your skin because they're big and clunky. Remember, they're pretty much a helium atom. If it does happen to enter the body, though, it can cause damage. So it's not going to enter your body through the skin, but you could somehow ingest alpha particles, and that could be damaging. We've got high energy radiation like beta particles. We've got high energy like protons and neutrons, which can travel into tissue and cause a lot more damage than alpha particles. So alpha particles, we kind of think of the big clunky ones. Higher radiation particles can do some serious damage. And then gamma rays, which are extremely damaging. They can travel a long way through body tissue and cause a lot of different abnormalities in cells. So here are some of the units again that we have available to us. So how do we get exposed to radiation? Because even right now, sitting at, you know, in your house, you're exposed to a background amount of radiation. There's naturally occurring radioisotopes in the material around us. So the ground, for instance, air, water, food, there's a small amount of radiation that's happening. We also experience a small amount of cosmic radiation, and just even like the materials around us is super, super tiny though, not anything we would notice. You can experience more radiation if you are in a medical field through x-rays, mammograms, different types of x-rays. Upper gastrointestinal x-ray is a pretty big dose. Some of these other ones, not so large. You only can't see them. Oh, your screen is paused. Hold on one second. Sorry. Let's try sharing again. How about now? Y'all good now? We're stuck on Geiger counter. Oh boy. Okay. Good now. All right, so there was our little Geiger counter. Okay, here are our units. This is a chart that has all the units and how they relate to each other. So you may, have to convert from one unit to another. Here's some of the different doses. Like I was saying, there's the upper gastrointestinal tract x-ray. That one tends to have more than some of the other ones. You can also get exposed to radiation through living by a nuclear power plant, but it's relatively small. That's because these things are heavily, heavily covered in lead and concrete, specifically so people don't get poisoned who live by them. Your television gives you a little bit. Radon is another one, radon gas. This comes up from the ground. That's why it's always good to get your basement. If you have a basement, get it checked for radon. Other things that can cause radiation, smoking cigarettes, cosmic rays, so on and so on. So radiation sickness, the larger the dose of radiation received at one time, the greater the effect on the body. And this LD50 value is the amount of radiation to the whole body that is lethal for half of the population. So half of people would survive, probably wouldn't be feeling very good, but half the people would die. And so we can see a dog is about 300 REM. So a bird would even be less. A human 500. So dogs will not fare as well in a nuclear holocaust as we will, but insects do really well, right? They need way more radiation than any human dog / rat needs to survive. An insect can even handle more radiation than a lot of bacteria. So a typical intravenous dose of iodine, 125 for a thyroid diagnostic test, because a lot of times they'll use these radioactive materials. They'll give them to you. You'll either ingest them or they'll give them to you intravenously, and then they can run machinery over it to see, to do some sort of like internal tracking. But let's say we have 100 microcuries. What is the dosage in megabarkals? So we've got, make sure you're using conversions for your prefixes as well. So I want you to do that one. And we know that 1 curie is equal to 3.7 times 10 to the 10 Becquerels. So you've got to get your microcurie into curie and your Becquerel into mega. Okay, so for this one, we would start with our 100 microcuries, and this micro can be converted into, we can ditch the prefix and go from a microcurie to a curie, knowing that one curie has 1 × 10⁶ microcuries. That's just using our SI prefixes. And then we can convert between curie and BQ by using this relationship here. So 1 curie is equal to 3.7 × 10⁻10 BQs. And then if we want to get it into a mega BQ, 1 mega BQ is equal to 1 × 10⁶ BQs. So that's just bringing back your prefixes. Again, for exams and stuff, you have access to those prefixes in your text, or you can have something printed out with the prefixes on it. Okay, so somebody asked about half-life. I think it was Lauren, or somebody in the chat was talking about half-life on the homework. So what is a half-life? Here's a picture of the Dead Sea Scrolls, and they were to determine the age of this using carbon-14, which is a radioactive material that degrades down to nitrogen. So when talking about a half-life, half-life is the amount of time, and it's dependent on the material, but it's the amount of time it takes for half of the radioactive material to become a more stable version, so to decay into a more stable material. So we start off with this purple here is iodine 131. It's the radioactive isotope. Sometimes this is called the parent isotope because it's what you're starting with. And then the green we're going to call the daughter isotope. So what happens is after one half-life, half of the parent has degraded or turned into or decayed into the daughter isotope. After 2 half-lives, the half of the half, or a quarter of the original, has now remained of the parent, and 3/4 of it has now turned into the daughter. After 3 half-lives, we take the half that happened before it, we cut it down into a half again, and then at this point we're at what, 1/8 of the original material is the parent. So let's say we started with 20 milligrams. This is a 20 milligram bar. After 1 half-life, it's turned into 10 milligrams of the parent and 10 milligrams of the daughter. After 2 half-lives, that 10 actually is going to get cut in half again. So we have 5 milligrams of the parent, and the remaining 15 are daughter. And after another half-life, the 5 gets cut into the half. We get 2.5 milligrams, and the remaining is the xenon. Here's what a decay curve looks like. So for iodine, this is going to be consistent for anything that's undergoing a half-life. So for iodine 131, we can see that right after 1 half-life, and in this case, it looks like a half-life is roughly equivalent to 8 days. So after 1 half-life, 8 days have passed, half of the original material is available. After 2 half-lives, or 16 days, a quarter of the original is left, and so on and so on. So because these are specific times, it's a consistent amount of time to go from a whole to a half, that's 8 days, and to go from a half to a quarter, it's 8 days, and to go from a quarter to an eighth, it's 8 days, and go from an eighth to a 16th, it's 8 days. Always this. We can actually then calculate how much time has then passed, right? Because if let's say we only have a quarter right here, a quarter of the original amount left, we can say 2 half-lives have passed, or 16 days. So what are the half-life values? You don't have to have these memorized, but here's some of them. Here's some naturally occurring radioisotopes. So carbon-14 has a half-life of 5,730, and you may want to have that number available for you during an exam. That's just a pretty common one. So half of the original radioactive carbon-14 will be present after 5,730 years. Because this is on sort of a thousands of year scale, this is a useful thing for anthropology. So a lot of times we use carbon dating, radiocarbon dating, when measuring things like the Dead Sea Scrolls or old pots or things, archaeological digs will use radiocarbon dating to measure the age of these materials because it's fits on the same magnitude. Potassium 40, okay, has a half-life of 1.3 times 10 to the 9th years. Okay, so this is in like the billions of years. Same thing with uranium. So I wouldn't want to age the old sea scrolls using these because this is such a big half-life. I'm not going to get the precision I need. Instead, I would use these to maybe age rocks or that are in like a mountain range to figure out how old a mountain range is, or to figure out how old a seafloor is somewhere, something on the hundreds of millions of scales. We're going to use this. As opposed to, I wouldn't measure the rock in the mountains here using radiocarbon dating, because after about 6 half-lives, 5 half-lives, it starts to lose its precision as far as aging. You can see that there are medical radioisotopes that we use, and these are relatively harmless. I mean, they're not something that you'd want to consume in high quantities every day, but once in a blue moon, if you're having some sort of scan, not a problem. And you can see all these things have half-lives of 28 days, all the way down to 6 hours. So these will move through your system very quickly and decay down. So how do we use half-lives? State the given and the needed quantities, always start with that. Write a plan to calculate your unknown quantity, write the half-life equalities and conversion factors, set up the problem and calculate the quantity. So there are specific half-life equations. Anyone in here who's taken like a geology class, or if you've taken, certain levels of math, you'll learn these equations. I'm not really going to have you do the equations. We're going to keep it pretty basic for this. So let's say there's the radioactive isotope strontium-90. Strontium-90 has a half-life of 38.1 years. If a sample contains 36 milligrams of strontium-90, how many milligrams will remain after 152.4 years? So again, there is an equation for this. If you know the half-life equations and you'd rather just plug it into the half-life equations, you can do that. But I'm going to walk through it kind of, I don't want to say it's the dumbed down version of this, but we're just simplifying it. So I have 152 years in total. I know that my half-life is 38.1 years. So I need to figure out how many half-lives have passed. All right, so if I have 152.4 years, I know that one half-life in this instance is equal to 38.1 years. So let's figure out how many half-lives have passed. So I take my 152.4 and I divide it by 38.1. And this tells me that 4 half-lives have passed, 4 1/2 lives. For this class, you're never going to get a half-life. Okay, that's when the equations come into play. It was when you have like 4.226 half-lives have passed. Well, in this case, only 4 half-lives. You only ever have like an integer value. So 4 half-lives have passed. So if I have 36 milligrams, how many milligrams would I have after 1 half-life? So let's go through half-life, 1 half-life. What do we do with our number 36? We're just going to cut it in half. So after 1 half-life, 36 divided by 2 is going to give us 18 milligrams. Okay, that would be great if we went through 1 half-life, but did we go through just 1 half-life? No, we have to go through a total of 4 half-lives. So let's repeat the process. So if I go again, okay, we have another half-life, 1 half-life. 18 will now become 9, right? We take the 18 and we cut it in half. We're not there yet. We've got to go through another half-life. So 1 half-life. 9 will become 4.5. And this is, sorry, milligrams. I'm ditching my units. No good. 4.5 milligrams. And then we actually need to go through one more half-life, right? We've done 1, 2, 3 half-lives. Let's do a 4th half-life. Okay, so this is another half-life. And we end up with, what, 2.25? 2.25 half. No, not half-life. What am I doing here? 2.25 milligrams. So when doing these problems, figure out how many half-lives have occurred, okay? And then just go through the process of dividing it out. That is going to get you through half-life stuff for this section. So figure out how many half-lives and then cut your milligrams from there. So we figured out that we had 4 half-lives, and then we just took our value and cut it in half and half and half and half. So carbon-14 was used to determine the age of the Dead Sea Scrolls. If the Dead Sea Scrolls were determined to be 2,000 years old, and the half-life of carbon-14 is 5,730 years. What is the fraction of this half-life that is passed? So this one, you're just going to take your 2,000 divided by the 5,730 and 0.3 half-lives have passed. But I'm not really going to ask you it in that capacity, so I wouldn't worry about that. Let's do this one, okay? So the half-life, or you do this one. The half-life of iodine-123 is 13 hours. How much of a 64 milligram sample is left after 26 hours? So calculate how many half-lives have passed and then half it out. Okay, so for this one, we have a total of 26 hours that have passed. So I start there, 26 hours. And I know that 1 half-life, in this case, is equal to 13 hours. The hours will cancel, and I can find that 2 half-lives have passed. So 2 half-lives have passed. We start with our initial sample. It's 64 milligrams. I have to go through 1 half-life. We take the 64 and we cut it in half, and we get 32 milligrams. But I need to go through 1 more of these. So we're going to cut it in half again. So 1 half-life. After another half-life, we end up with what? 16 milligrams. Do this here. 32 would have equated to 1 half-life. This would have equated to 3 half-lives. Any questions on that? Help it make a little more sense for that last question on the, bring it up here. Here where it said, we've got this material, it's radioactive. So it says it has a half-life of 6 hours and is a pure gamma emitter. Suppose that you have 80 milligrams to start with. How many milligrams would remain after each of these? 1 half-life, 2 half-life, 18 hours, which is just the same thing as 3 half-lives, and 24 hours, which would be the same thing as 4 half-lives. So you will just go through the process of taking your value, whereas at the 80 milligrams, cut it in half for this one, cut it in half for this one, cut it in half, and then cut it in half. So some of the applications, medical applications of radioactivity, and some of you may be going into these fields or be using some of this equipment. We can use radioactive isotopes to scan the body to look at different sorts of things that maybe are accumulating in organs, thyroid, body areas. So radioactive isotopes with short half-lives are used in nuclear medicine because the cells in the body won't differentiate non-radioactive atoms and radioactive atoms. And once incorporated into the cells, the radioactive atoms are detected because they emit radiation, giving an image of the organ. So you consume this radioactive material in some way, and it will get digested by your body in the cells of your body. And then once it's in your cells, it will emit different types of radiation, and then a piece of equipment will absorb that radiation, and it'll make a picture of the soft tissue of your body. So here's a bunch of different types of isotopes and what you'd use them for, different types of, all sorts of different types of things. A lot of use in a lot of different cancers, like measuring and imaging cancers. So after a radioisotope is ingested, the radiologist determines the level and the location of the radioactivity that's emitted. The scanner will move over that given organ. It will scan all of the different gamma and beta rays that are coming off of it, and it'll start to create an image of the organ. So here they are, it looks like they're scanning her throat, so probably her thyroid, to see if it, I would guess to see if she's got an overactive thyroid in that case, or if there's any sort of cancerous lumps in the area. So if you've heard of a PET scan or a PET scan, oh, I got to get a PET scan. This is positron emission tomography. So that's what that P stands for. In this instance, they will use a couple different things, but they can use fluorine 18. You ingest that and it will release a positron, and then what's left over is this oxygen 18, which is, it's not going to do anything to you. So, you know, harmless stuff. But this positron is what will then end up hitting some sort of receptor that will then image in 3D the organ that they're talking about. This can be used for a bunch of different things like brain function, metabolism, and also blood flow. So you can use this to check in on blood movement in the heart. There's an image of a PET scan for a brain. And it looks like on the left, they have a brain, a normal brain, and then a brain on the right that is, this person is going through Alzheimer's. So you can see there's a lot more activity here, a lot more movement and blood flow versus what's happening here, less brain activity. So then you get this computed tomography or this CT scan. So we have another imaging method, and in this case, this will use X-ray beams, and it will help to sort of show us the different layers, so we can actually see multi-layers of whatever we're looking at. In this case, they're looking at a brain to see if there's fluids, any weird like tissue density things or difference in tissue densities for tumor. We have magnetic resonance imaging, or MRI. This is an imaging technique. It doesn't involve any sort of X-ray radiation. It's the least invasive of any of the methods available. And in this case, it's based on the absorption of energy when protons and hydrogen atoms are excited by some sort of magnetic field. So they stick you in a giant magnet. They create a magnetic field, and all these protons in your body get excited, and then they're able to read them to get images. So they can excite different areas of the body. That's why if you're ever getting an MRI, you know, they always ask you, do you have a metal plate in your head? Make sure you take off all your jewelry. Have you been shot before? Do you have shrapnel in your body? Because you definitely don't want to go into an MRI machine if you have metal in your body somewhere. Here's an MRI of, well, we got the pulmonary system. So we've got the lungs and then the heart. So I'm not going to test you on which of the isotopes are better for nuclear medicine. Don't worry about that. Okay, the last thing that we'll talk about is, let's see where we're at in time. We should get through it. Nuclear fission versus fusion. So in the 1930s, scientists started bombarding uranium-235 with a neutron. And they discovered that this uranium-235, the neutron would sort of stick its way into the uranium-235. It would become very unstable, and then it would split and break into smaller nuclei. And then it would actually release more neutrons as well, and it would create a bunch of energy, a large amount of energy. So in nuclear fission, FISSION, we have a large nucleus. It's bombarded by a small particle, and it splits it into a smaller nuclei, and then also will produce some more smaller particles like neutrons. This releases a lot of energy called atomic energy. Anytime you're splitting atoms, you're going to produce a lot of energy. When we take the neutron and we bombard uranium-235, the unstable nucleus, which is now 236, right, because we threw a neutron in there, will undergo fission, and fission meaning it splits. So fission to split, fusion means we bring them together. And then we get this krypton-91 and barium-142. So here is an image of a typical nuclear fission reaction, which we had just seen, but here comes the neutron, boom, it hits into the uranium-235, it makes it unstable. So there's this sort of intermittent step here. We've got this, now we have this highly unstable nuclei, and then it will decay into these smaller, and atoms, and then we also get 3 neutrons and a bunch of energy. This energy is what we capture in like a nuclear fission reaction to make electricity. We've got a nuclear power plant. Now this system will create what's known as a chain reaction. And so a chain reaction is when we start a reaction, and then that reaction allows other reactions to move forward, splitting more and more and more, and it increases exponentially. So this first neutron, right, it was just 1 neutron, it hit the uranium, it split into the 2 smaller atoms, and then it produced 3 neutrons. So we got 3 neutrons from an initial 1 neutron. What happens to those 3 neutrons? Each of those can hit another uranium that happens to be surrounding. It's producing energy. When it bumps into these, it makes those unstable. Those will split and then produce energy. And what we're finding is that here we had 1 little bubble of energy. Now we have 3 bubbles of energy. Next time we'll have 9 bubbles of energy, and we continue exponentially, so on and so on. And so the reaction speeds up as we move down the system, and the reaction itself propagates until we run out of uranium to hit. If we have fission, we also have to have this thing called nuclear fusion, which is when we take 2 smaller nuclei and we turn them into 1 large nuclei. So we can synthesize this in a couple different situations. There's this, what is it called? A tomac, I think. It's a very high temperature, high pressure situation where we're able to take these 2 things, smush them together. And nuclear, when they talk about like free energy and pollution-free energy and running all of the world on, a packet of water, they're talking about nuclear fusion. And this is what happens in stars, okay? So there's so much heat and there's so much pressure in a star, it can take 2 hydrogens and smush them together into a helium, right? And then it'll produce a neutron and a lot of energy. Like we're talking a lot of energy. This is continuously happening in stars. Stars start as hydrogen, they make helium, and then, sometimes the heliums will come together and they'll make something heavier. And so a lot of the elements up till about iron are created in stars. So all the material that our bodies are made of came from stars. After about iron 26, those bigger atoms come from like supernovas, from like star explosions. So this would be a great way. There's no like, look at what our product is here. I mean, it's helium. We're taking hydrogen and our product is helium and a bunch of energy. Helium is inert. It's not a bad byproduct, right? When we're combusting fossil fuels, what is our product? Our product is CO2. Here we're getting helium and we're getting all this energy. So it would be really great if we could make nuclear fusion happen. They're trying to make nuclear fusion happen. The problem is that it has to occur at very, very high temperatures. In a fusion reaction, there's a large amount of energy that's produced. And the only thing that your waste is really is helium. So there's a lot less waste. But we aren't there yet on nuclear fusion, okay? That's kind of a pipe dream for physicists. Someday maybe we'll get there, but not there yet. So indicate whether each of the following describes nuclear fission or nuclear fusion. Fusion, remember, to fuse. Fission is the opposite, to split. So a nucleus splits will definitely be fission, all right? Large amounts of energy are released. That's fusion and fission. Both of them produce a lot of energy. Small nuclei form a larger nuclei. That's to fuse, fusion. So that's what we would see happening in stars. Hydrogen nuclei react. That's also in fusion. We have two hydrogens that come together. Several neutrons are released. That is fission. Fusion does have a neutron that's released, but to get several neutrons, we see that in fission. So know the difference between fission and fusion, basics. Let's look at this here. I want you to complete this equation. So supply the missing atomic symbol to complete the equation for the following nuclear fission reaction. So we've got uranium-235. It's getting smacked with a nitrogen. No, it's getting smacked with a neutron. And we get Te-137, some sort of mystery particle, and 2 neutrons, and then energy. Remember that this is take note that this is 2 neutrons, okay? So you're gonna need to double up your number on the top. Ashley, the dry lab and you'll have 2 assignments due. You'll have the dry lab due, and then you'll have a lab due out of the lab manual. They're both on nuclear chemistry. They'll both, you just turn them in like back to back, like almost like you had them all stapled together. And they will be due, I believe they're due on Sunday. Okay, so top numbers need to equal each other. Bottom numbers need to equal each other. We had 235 plus the 1 gives us 236. All right, on this side, we had 137 in the TE, and we had 2 in this area here for the neutron, because we need to multiply it by 2. So this number should actually be 97 as opposed to 98. Take the 2 into account. On the bottom, we needed 92. 52 of them were being occupied here. 0 of them were being occupied here. So we had a 7 here. So it's zircon 97. And that's it for nuclear chemistry. So that's all we've got for today. If you've got any questions, feel free to stay around, chat. Otherwise, enjoy the rest of this rainy afternoon. I will see you all next week. Bye.